Alright, so I'm going to start with number 3. A cyclist rides 8 kilometers east for 20 minutes. Then he turns and heads west for 8 minutes and 3.2 kilometers. This is worded horribly. I don't know why. But anyway, finally he rides for 16 kilometers, which takes 40 minutes. Then B is what is his average velocity. And also, technically for B, we're also solving for A, but you can just do it all in one step, so it doesn't really matter. So first, let's map this out. I'm going to draw a compass real quick. So first, he rides 8 kilometers for 20 minutes, I believe. Yes. Okay. So first, we're going to draw that. So he goes east for 8 kilometers and 20 minutes. And then he goes west for 3.2 kilometers and 8 minutes. So let's do 3.2 kilometers. Okay, hang on. Let me just that's right here. And then he goes east again. Actually, it doesn't say his sex. I got he or she or they go. Oh, it does say his sex. Never mind. Uh, 16 kilometers for 40 minutes. So let's go 16 for 40 minutes. All right. And he also turns back east when he does that. So basically what you're going to do for average velocity is you can just do the displacement, the total displacement divided by the total time that U is moving. So to get the total displacement, you just do 8 kilometers plus 16 kilometers, which is the amount that he goes east in the positive x direction, and then minus 3.2 kilometers, which is the amount that he goes west, which is the negative x direction in this instance. And then that's going to be over the time that he traveled, which is just 20 minutes plus 8 minutes plus 40 minutes. So 20 minutes plus 40 minutes. Okay, no. Hang on. I'm just... okay. There we go. Alright. 40 minutes. Plus 8 minutes. And then after all of that, you're going to get, let's see, 8 plus 16 minus 3.2 divided by 20 plus 40 plus 8. And you're going to get 0.3058. And that's going to be in kilometers per minute. So now all you need to do to get your final answer is to just convert kilometers to minutes to meters per second. So what you're going to want to do, okay, no, not that, don't do that, is just, or this is at least in my opinion, the least mistake prone way of converting units is just writing out what you have and then doing like this, like a line, and then on the top you have kilometers, and since it's being divided by minutes, it's bottom you have minutes, and then you just convert. So on the bottom, I'm going to have 1 kilometer because I want to get rid of that kilometer unit. So I would divide this kilometers by this, and then that would get rid of it. And then 1 kilometer up here is equal to 10 cubed, which are 1,000 meters. And then up here, I would just put, I want to get rid of the minutes. So I'm going to put 1 minute here, and that's going to be equal to 60 seconds. And also for time, if this were like in hours and not minutes, I would just put 3600 seconds instead of 60 seconds. It's not worth it, in my opinion, to convert from hours to minutes to seconds. You could just divide it by 3600 and then get, do it all in one move, I guess. But anyway, so now you basically just multiply everything on the top and then divide everything on the bottom. So you have 0.30588 times 10 cubed. So times 1,000. No, hang on. Times 1,000. And then divide it by 60. And then you're gonna have 5.098. Okay, now 98 meters per second, which I think in the answer key it's really weird. Yeah, it's so you round this, and then it becomes 5.11. So that, yeah. Anyway, that's the answer for 3B. I'm gonna take a look at the next problem. All right, so for 12, we have a woodpecker's brain is especially protected from large accelerations by tendon-like attachments inside the skull. While pecking on a tree, the woodpecker's head comes to a stop from an initial velocity of 0.6 meters per second in a distance of only 2 millimeters. Find the acceleration in meters per second squared in multiples of g, where g equals 9.80 meters per second squared. I don't know why they put 9.80, because g equals 9.81. Like, if you want to round to 9.8, that's fine, but I don't know why you would add the 0 when it's supposed to equal 9.8. Okay, well, anyway, calculate the stopping time. The tendons cradling the brain stretch, making its stopping distance 4.5 millimeters. Greater than the head, and hence less acceleration of the brain. What is the brain's acceleration expressed in multiples of g? All right, I'm gonna map this out real quick. Okay, so I started with hang on, actually, let me. Okay, sorry, my Spotify was being evil. I started with 0.6 meters per second is the initial velocity that the woodpecker's head was at, and then it says that it came to a stop. So the woodpecker's head come to a stop from initial velocity, so that means that the final velocity is going to be 0, and then it also says that its head moved 2 millimeters. So there's a few ways you could do that. I kind of just did like its head moved this way 2 millimeters, and then it stopped. So that kind of implies that this would be x initial would be 0 here, and then x final right here would be 2 millimeters. Okay, well, or whatever. Either way, because you could also make it so that like it's right here at x initial it's negative 2 millimeters, and then it moves over like to 0. But I figured that would probably be harder or more annoying to do, just dealing with a negative number there. Anyway, the first thing I want to do is I want to convert this x final here to 2 millimeters, because for part A, or not 2 mil, I want to convert the 2 millimeters into meters, because for part A it asks for the acceleration. It asks for the woodpecker's like head's acceleration. So the first thing I want to do, because we're going to have to use one of the kinematics equations, is I want to convert this into meters so that I don't have to worry about everything else is in meters, and that's just the standard. So, I don't have to worry about stuff later. Oh, yeah, dealing with that. Anyway, so what I'm going to do is I'm going to have 1 millimeter. Okay. And that's going to equal 10 to the negative third meters. And then the millimeters are going to cancel out, and then it's going to be in meters. And then 2 times 10 to the negative third, which is just 2 divided by 0.001. So, and that's gonna be 0.002. All right. So that's x final is gonna be 0.002 meters. You can also write that in scientific notation. I'm choosing not to. And then it's just asking for the acceleration for part A. So just A equals question mark, and now we just find the acceleration. So you look at the kinematics equations, and we look at what we have. Notice that it never gave us a time, which is usually a pretty important thing to have for a lot of stuff. And also time is included in this one and this one. And since we're solving for acceleration and not time, we can't really use either of these, which means we have to use this one, which has v final here, which we have, v initial here, which we have 2. I don't know why I mentioned the 2. Okay, it has acceleration, which we're solving for, and then it has x final, which we have, and x initial, which we also have. So that means that we can use this this equation here. So we have v final squared equals v initial. Okay. V initial squared plus 2a times x final minus x initial plus 2 times a times x final minus x initial. And now let's look at some of this here. We have v final equals 0, so I'm just going to have this as 0. And then we have x initial is 0 as well, so this is just going to be v initial 0 equals v initial squared plus 2a times x final, and then that's going to imply that negative v initial squared, which so the v initial squared is going to come out negative because it's more like this, just in case you're wondering, because sometimes people get confused about, oh, but if it's squared, does that get rid of the negative? And not in this instance. No, it would if you're plugging in a negative number, but since we're not, it doesn't. It's not negative. Anyway, negative v initial squared plus equals 2a times x final, and then so we're just gonna have a equals negative v initial squared all over 2 times x final. And now we just plug in the numbers that we have. So v initial is 0.6 meters per second. So negative 0.6 meters per second squared times all over 2 times x final. So 0.002 meters, and then that's gonna equal we'll just do so 0.6 squared times -1, so negative 0.36 divided by 2 times 0.002, and then that's gonna be negative 90 meters per second squared. I'm trying to make sure. Yes, okay. I wanted to make sure the units were correct. This would come out as meters squared over second squared, and then the meters would cancel out, and then it would just be meters over second squared, which is what we have. And then, so finally, this would be the acceleration, but it wants it in terms of g, which g in this instance is 9.8 meters per second squared. So basically, after all of that, we just do negative 90 over negative 90 meters per second squared divided by 9.81, and then that's gonna equal negative 9 point, well, meters per second squared, my bad. 9.174, and then put G, and that should be the answer to part A. Yeah, okay. Yeah, 99.8. I think it made this positive, which I would agree with because G is usually negative. Well, I guess it doesn't really matter. But in this instance, it's not, so I don't know. But either way, this is correct, the negative 90. They also rounded wrong here. I also, I would like to point out on number 3, I think they rounded wrong as well. I said that they didn't, but I think I was just coping. Yeah, no, I don't even think I did say. I'm pretty sure I just said it was weird, but I meant that they were wrong with the rounding. I'm pretty sure. But yeah, I don't know. Because it's 9.174. Yeah, and I don't think I cut corners anywhere, so I'm pretty sure the rounding's just wrong. But either way, we know this is right for sure. So this is right. Anyway, for part B, calculate the stopping time. So now we're going to calculate time, which we can do with the acceleration. So here, let me write that out real quick. Also, I said the rounding was wrong. It actually wasn't. When I put G in, I divided it by 9.81 instead of 9.8 because I am very used to using 9.81 as G instead of 9.8. So that was my bad. Because G does equal 9.81, and they also rounded it to they rounded it to 2 digits here, but they didn't put the 1. I don't know what that's for, but it's fine. Anyway, so that was my bad. The rounding on this is probably correct, just because 9.1743 is very close to 9.18 for like being able to round to it. So it was probably fine. Anyway, it wants the stopping time, so which is just the time that it takes for it to stop. So and now we have the acceleration, so we should be able to use actually I was going to say this equation. We can use this equation for it, time, which was much easier to use, or just less complicated really. So we have v final equals v initial plus at. So v final, this is part B, by the way. I already read it out, but just so I'm extra clear on what I'm doing here. V final equals v initial plus at. Let me make sure that's correct. Yep, good. And then we just have to solve for time. So v final minus v initial all over a equals t. And then that's we just have to plug it in, so that implies t equals v final, which is 0. I probably should have paid attention to that earlier. So negative v initial, which is 0.6, so negative 0.6 meters per second all over a, which is negative 90 meters per second squared. Yeah, okay. And then I just have to plug it into the calculator. So 0.6 divided by 90. Oh, that sucks. I mean, I kind of knew that was going to happen, but what does it say here? It's probably in scientific notation over here. Yeah, it is. Okay. Anyway, that's going to equal 0.6, no, 0.00667 seconds, and the units work out, the meters cancel out, and then one of the seconds cancel out, and since the second is like a fraction underneath a fraction, it goes back onto the top. So the units work out here, and then this is just going to be you can just move the decimal point 1, 2, 3 places over, so that's going to be 6 times 6.67 second, times 10 to the third power, because you move it 3 times over to cubed. All right, and that's going to be seconds, and then that's your answer for the stopping time. And yeah, oh, okay, it's to the negative third. Yeah, it's to the negative third power. That was my bad. Yeah, it's to the negative third power. Okay. All right, so that's part B done. Circle it. So now for part C, the tendons cradling the brain stretch, making its stopping distance 4.5 millimeters. Okay, wow, that's over double. Greater than the head, and hence less acceleration of the brain. What is the brain's acceleration expressed in? So we're just doing the same thing as part A, but instead of 2 millimeters being x final, it's 4.5 millimeters. So we'll do that real quick. Let me pause this. So for part C, we have all the same numbers except for the x final here. Instead of 2 millimeters, it's 4.5. No, hang on. Where is, there it is. All right, so it's 4.5 millimeters. And so let's convert that. Okay, well, we take those, I guess. Let's convert that into meters real quick. So 4.5 millimeters. And then that's going to be 1 millimeter. Then over that's going to be 10 to the negative third meters. And then we just have 4.5 times 10 to the negative third. No, hang on. All right. Yep. All right. And that's going to be 0.0045. Which you don't really need a calculator for, but I'm just doing it on instinct, I guess. I don't know. And also, it prevents mistakes. 0.0045 meters. And so now we have x final. Okay, we have x final. And so we just do the same thing we did for part A, but with this instead of 0.002. So we're solving for acceleration and in terms of g. So we just use we just use this equation again. So I'll set that up real quick. All right, so we start off with v final squared equals v initial squared plus 2a times x final minus x initial. And then v final is 0 and x initial is also 0, so it just becomes v initial squared plus 2a times x final equals 0, and then it's negative v initial squared all over 2 times x final, that equals a. You just plug it all in, you get negative 40 meters per second squared. And then to get it in terms of g, you just do negative 40 meters per second squared divided by 9.8 meters per second squared, and then you get 4.082 times g, which is the answer. So that's how you do number 12. Then we'll move on to number 16. A coin is dropped from a hot air balloon that is 300 meters above the ground and rising at 10 meters per second upward. For the coin, find A, the maximum height reached, B, its position and velocity 4 seconds after being released, and C, the time it takes before it hits the ground. All right, so let's start with A, the maximum height the coin reaches. All right, so I sketched out like the moment that the coin is dropped, and so the balloon is 300 meters per second no, the balloon is 300 meters in the air, which means that just means the coin you have to assume is also 300 meters in the air, and then the balloon is traveling 10 meters per second upward when the coin is dropped, which also means that the coin will be traveling 10 meters upward, or 10 meters per second upward when it's dropped as well, which means that the maximum height, which is what we're solving for in part A, is not going to be 300 meters. It's going to be a little bit more than that because it's going to be traveling up at 10 meters per second when it's dropped, but it's going to have the acceleration of gravity pulling it down, which will eventually make the velocity go from 10 meters per second to a negative velocity that makes it fall to the ground. So, the way we figure out what the maximum height of the coin is basically when the velocity equals 0, because that means that the negative acceleration from gravity makes it so that that's like the exact point that the velocity is no longer positive and going up. It becomes like negative, so it starts going down. So when it's 0 would be like the highest point of the coin because it hasn't become negative yet, and it's done being positive. It's done going up. So with that information, and I find this makes this a little bit easier. We just write down what we know. So we know that the initial velocity of the coin is going to be 10 meters per second because that's the velocity of the balloon when the coin is dropped. And then the initial position of the balloon is going to be 300 meters. And the final velocity of the coin, which is in the moment, which is basically the final velocity would be like the velocity of the coin at the moment that it reaches its maximum height, because that's what we're solving for. So basically all of this is like the final stuff is the moment it reaches maximum height, whereas the initial stuff is where it starts. So the final in this instance is going to be 0 because when it reaches 0, it's not going up anymore and it hasn't started going down yet. So that's like the maximum. And then we're solving for we're solving for y final here, because that's, like I said, the final velocity, the final position. That's the maximum height, because it's the final y position before it starts like falling down would be up here, and then it's gonna start falling down. So we're solving for y final, and then let's see. Does it give us anything else? 300 meters above the ground, 10 meters per second upward, and it's dropped. So it's dropped 300 meters, and all right, and then maximum height. Okay. So with that, let's just take a look at our formulas here. Right, so I forgot to add that when the coin is falling, I remember there was one more thing I wanted to write down, but I couldn't think of it until I started solving the problem in my head. When the coin is falling, its acceleration is going to be the acceleration of gravity. So that's going to be negative 9.81 meter. Okay. Negative 9.81 meters per second squared. And negative 9.8, negative 9.81 doesn't really matter too much. But this is going to be the acceleration of a falling object on Earth. If there's nothing else like pushing on it, any object that's just free falling on Earth is going to have this as the acceleration. And obviously what's the word? We're not thinking about air resistance. Air resistance is not being accounted for here. It doesn't really matter if it is. It's not that big a deal. I think it'd be off by like a little bit if you accounted for air resistance, which we couldn't do anyway. It's too much work, and it's not really much reward. Air resistance doesn't matter. Anyway. For this, we can just we can use this formula. We can use this formula here. At first, I thought we were gonna have to solve for time, which we probably will at some point. But for now, for this specific equation, we don't have to solve for time. We can just do it. We can just use this one. which we used for number 12 as well. So we have v final squared equals v initial squared plus 2a times x final minus x initial. Yes, okay. Y final minus y initial. I have it, the variable as y for position instead of x because it's we're doing it. We're solving for like vertical position instead of horizontal. It doesn't really matter which variable you use, but traditionally you want to use y for vertical and x for horizontal, just so you know it shows you're aware of what you're doing here. But v final is gonna be 0, so 0 equals v initial squared plus 2a times y final minus y initial, and then and then we're just going to solve for y final here, and that'll give us the maximum height. So here, I'll just do that off screen. Okay, so we have negative v initial squared, which you subtract v initial, and then you divide by 2a, and then you're left with y final minus y initial. So then you just move that y initial over to the left side, so then it becomes negative v initial squared divided by 2a plus y initial, and that's going to equal y final, and then we just plug in all the numbers to solve for y final, and that'll give us the maximum height. So we have y final equals negative 10 meters per second squared, and all over 2 times negative 9 meters. Oh, sorry, no, not negative 9. 9.81 meters per second squared. Plus y initial, which is 300 meters. That says 30. Okay, there we go. And so now we just plug it into a calculator. So 10 squared is 100, and then divide that by 2 times 9.81, and then add 300, and we should get 305.10 meters. So for number 16 we have 305.1, so that should be the answer, and that's what we have. So that's going to be part A of number 16. So now let's move on to part B. All right, so for part B, we're going to have to find its position and velocity after 4 seconds, or 4 seconds after it was released. So I erased the units or the stuff that it gave us, because some of it we can keep and some of it we have to get rid of, so I might as well just write it down again so that we know. So first, it's given to us that it's 300. The initial position is 300 meters. And okay, well, hang on. All right, 300 meters. And then it's given to us that the initial velocity is 10 meters. Because the balloon's going 10 meters when it's dropped. Or 10 meters per second, sorry. It's going 10 meters per second. Not meters, it's going 10 meters per second when it's dropped. And the acceleration is negative 9.81 meters per second squared, because any object in free fall on Earth has an acceleration of negative 9.81 meters per second squared. All right, and finally, it gives us, in this problem specifically, that time t equals 4 seconds, because it wants the position and velocity 4 seconds after being released. So t equals 4 seconds. And now we know that it wants v final and y final, because it wants the position and the velocity and it's, so this is initial is 0 seconds after being released, so then final is going to be 4 seconds after being released. So y final equals question mark, and v final equals question mark. And so now let's look at the kinematics equations and see which ones we can use. So we're solving for final velocity and final position. We could, I'm trying to see, we could use potential. Hang on, let me just look at it off. Okay, so we're gonna start with this. We're gonna solve for v final here. So v final equals v initial plus at, and then we just plug numbers in. So that's gonna be v final equals 10 meters per second plus negative 9.81 meters per second squared times 4 seconds. And then you plug that into a calculator, you're going to get negative 29.24 meters per second. And then over here in the answer key, it's negative 29.2 meters per second. And then for position, originally I was going to integrate this, just use calculus, integrate this, and then to get the position, because I was like, oh, it'll probably be faster than using this. But then I realized that this formula is literally this integrated, and I was like, oh, never mind, it's not faster. It's the same exact thing, but with an extra step added. So we're gonna solve for position now, and we just do the same thing as we already have all of these variables, so we can just plug it into the formula, and then we can solve for position here. And the we don't even have to do any algebra. The formula literally solves for like the final position, so we can just y final equals y initial plus v initial times t plus 1/2 at squared. And so now we can just that's gonna equal 300 meters. Okay, that does not, there's no, hang on, let me write meters. Plus v initial, so 10 meters per second times 4, 10 meters per second times 4 seconds plus 1/2 times negative, okay, 9.81 meters per second squared times 4 seconds squared. And you plug that into a calculator, and they'll just do it. Nope. And if you plug that into a calculator, you get 261.52. And then the answer key, it's 261.6. Oh, meters. Okay, my bad. There we go. 261. And the reason why my answer is different again is because I'm stubborn and I used negative 9.81 and not negative 9.8. But if it gives you A, then yeah, I would have used 9.8. Or if it gave you G, or like the acceleration, I would have used negative 9.8. But it didn't give it to us, and I'm stubborn, so I added the 1 here. But for future reference, if you're doing one of these problems, don't use negative 9.81. Just use negative 9.8 because this class, every instance that we use g as a constant, it's not going to have the 1 here. But the 1 is a little bit more accurate. And it was a little frustrating on 3 because they added the 0 at the end for no reason because it doesn't even equal 9.8. Or was it 3? Oh, wait, was it 12? Yeah, it was 12. Yeah, either way, they added the 0 at the end. I don't know why. There's no 0 here. It's a 1. But anyway, that being said, that's a kind of a useless thing to complain about. We can move on to C now. So, so for C, it just wants the time before it hits the ground. So it just wants the time that it's going to hit the ground. We're just going to be solving for time, and here, let me write down the stuff again. So this time I kept our givens, so it's given to us that y initial is 300 meters, and v initial is 10 meters per second, and a is going to be accelerating at a negative 0.81 meters per second squared. And so when it hits the ground, because that's what it wants to solve for the time when it hits the ground. We already know that the y final is going to be 0 because when it hits the ground, that's 0 right there. This is 300 meters. This is 0 meters. So y final is going to equal 0. And it wants, I think that's it. So we should be able to just solve with this information. Yeah, actually, I don't see why not. That should be fine, because we can just use this here. Yeah, we can just use this here. And you can just do y final equals, we have y initial, v initial, and a. So yeah, we just use this and solve for t. So we know y final is 0. So y final equals y initial plus v initial times t plus 1/2 a t squared. And so now we know y final is 0, so 0 equals y initial plus, nope, that's okay, plus v initial times t plus 1/2 a t squared. And so now, to solve for t, pretty much just want to do a quadratic formula. So that's going to equal, so just write this out, 300 meters, let me do it down here so I actually have room. It's going to equal 300 meters plus v initial times t, so plus 10 meters per second times t, and then plus 1/2 times a. So I'm just going to do it in the calculator now. 9.81 divided by 2, so that's going to be negative 4.905. So I'll do minus 4.905 t squared. And now we just do the quadratic formula. I'm going to, I guess, rewrite this so that it is an actual quadratic equation. Oh, wait, I forgot to write meters per second squared. It's fine. We'll do it here. So negative 4.905 meters per second squared times t squared plus 10 meters per second squared plus 300 meters And then we're just going to do the quadratic formula, which a quadratic equation is going to look like ax squared plus bx plus c, and that's like a basic fundamental quadratic equation. So like a would be negative 4.905 meters per second squared, and then x squared is t squared, and then I forgot to put a t here actually, but and then b would be 10 meters per second. Oh, it's not 10 meters per second squared. I am like screwing up all over the place. Sorry, I'm very tired. All right, let me just. All right, so b would be 10 meters per second. Oh, okay. And then times t, and x is t, and then c would be 300 meters. So and then the quadratic formula is basically you use it to solve for x. In this case, it'd be t. So it's the quadratic formula is going to be x equals negative b plus or minus the square root. And since for a quadratic equation, and basically because the quadratic equation or quadratic equation is always going to equal 0. So you're basically solving for x when x equals 0. So basically it's just x equals negative b plus or minus the square root of b squared minus 4ac. And I figured you probably know this from like algebra and maybe calculus or all over 2a, but I was doing that. And I figured you probably already know this formula and like what a quadratic equation is already, but or a polynomial, I don't. I just figured I'd show you just in case. So now I can solve for x or for t, because t is x in this instance, and it's plus or minus the square root because you're always gonna have two x's that make this equation equal 0. So now I can solve for t. So t is gonna equal negative b, which is going to be negative 4.905, which I'm just going to make into positive 4.905. Meters per second squared time plus or minus the square root of b squared. So oh, I put okay. I'm sorry. I'm like screwing up this like last problem, but okay, yeah, it's not negative b. It's not negative 4.905. It's negative 10. That's the eraser tool. Hang on. It's negative 10. It's not negative, or negative b is negative 10 plus or minus the square root of b squared, which is 100 minus 4ac. So that's gonna be minus 4. Minus 4ac, so that's going to be minus 4 times a, which is this, and c, which is the 300. So I'm just going to do that in my head. So it would be negative 4 times this negative here, so it's going to be positive, so it's going to be 4 times 4.905 times 300, and then just plus, so 100 plus 5, 8, 8, 6, all over 2 times a. And I kind of gave up on putting my units. You shouldn't give up on putting your units, but I'm running out of room and will to put my units down, so it's fine. All over 2a, which is this is a here, and this example of the equation. So not to a, as like the acceleration is this, but in the quadratic formula for this, it's okay. You understand probably. times all over 2a, so 2 times negative 4.905. And basically, when you're doing the quadratic formula for like in like physics for like solving for time, one of them is going to be negative. Like one of your answers is going to be negative because it's plus or minus the square root, which means you have two different answers. So one of your answers is going to be negative and one of them is going to be positive. You just take the positive one because there's not going to be a negative time. So in this instance, the negative or the positive answer is going to be negative 10 minus this square root because you're dividing it by a negative number down here. So yeah, so basically square root of 100. I'll do it on my calculator real quick. 5886, 100 plus 5886. Take the square root, and then just add 10, and then divide by 2 times 4.905. And that should be 8. Okay, that's not an 8. Hang on. 8.906 seconds. And we can check 8.91. Yep. All right. So that's going to be the answer to T, and that should be all the problems. Yep, that was 16C. Okay. So let me know if you need help with anything else, and if I can, if you need like more explanation for any of these problems, let me know. I'm happy to help. But otherwise, good luck, and let me know if you need anything.